Hello, everyone. Welcome to Task 1, Entering the World of PLC. Against the backdrop of rapid industrial automation development, PLCs, as core control devices, have penetrated every corner of production. In this lesson, we will explore the origin, principles, characteristics, and future trends of PLCs, helping everyone progress from a basic understanding to a deep comprehension of this industrial control brain. Next, let's begin today's learning journey. This task must be completed in teams. Study the textbook and research materials. Systematically trace the technological evolution of programmable logic controllers, PLCs. Clarify their core mechanisms, technological transformations, and application scenarios. Finally, a representative will present the working principle. The presentation must be precise, rigorous, and concise. Knowledge objectives for this lesson. First, understand the origin and development history of PLCs. Second, master their definition, basic components, and working principles. Third, comprehend the developmental path from relay control to modern intelligent controllers. Fourth, become familiar with the new roles and application fields of PLCs in Industry 4.0. Skill objectives. After learning, be able to independently research and outline the history of PLC development, fluently explain their working principles with examples, and illustrate specific applications with practical scenarios. Quality objectives. Cultivate professional habits of engaging in technical activities according to standards. Develop engineering thinking to understand the industrial demands behind technological iterations. Establish safety and specification awareness, and focus on the standardization of PLC programming. To understand PLCs, we must first know their past life. Before PLCs were born, industrial control mainly relied on relay contactor control systems. These systems were inexpensive and structurally simple, easy to operate and maintain, and were widely used initially. However, as industrial production grew more complex, their drawbacks became evident. Large size, poor reliability, slow response, limited functionality, complex wiring, leading to high failure rates. When production needs changed, modifying the control logic required rewiring, which was costly and made complex control difficult to achieve, resulting in poor versatility and flexibility. For example, adjusting processes on an automotive production line might require laying a large amount of wiring in a relay control system, a time-consuming, labor-intensive, and error-prone task. These pain points spurred the birth of the PLC. By 1968, the pain points of industrial control saw a turning point. That year, General Motors, GM, in the United States proposed requirements for developing a new type of controller. These requirements directly drove the birth of the PLC. Let's take a look at GM's specific requirements. Let's all think about the industrial pain points behind these demands. First, simple programming. It allows on-site program modifications, solving the rewiring issue for logic changes in relay control systems. Second, easy maintenance. Plug-in type is preferred, reducing difficulty in troubleshooting and repair. Third, higher reliability than relay control panels, reducing production downtime. Fourth, smaller size than relay control panels, saving workshop space. Fifth, ability to send data directly to management computers, enabling data-driven production management. Sixth, cost competitive with relay control panels, ensuring economic viability. Seventh, input compatibility with 115 volts AC, adapting to industrial power environments. Eighth, output of 115 volts AC, 2A or higher, able to directly drive solenoid valves, meeting on-site equipment drive requirements. Ninth, minimal changes to the original system during expansion, improving system flexibility. 10. User program memory expandable to at least 4 kilobytes, meeting complex control needs. These requirements accurately targeted the shortcomings of relay control systems and set the direction for PLC technology. With clear requirements defined, the birth of the PLC entered the fast lane. Let's look at the timeline of the PLC's birth. 1968, General Motors, GM, formally proposed a requirement for a new controller, becoming the spark that ignited PLC development. 1969, Digital Equipment Corporation (DEC) responded, developing the world's first PLC, initially called the Programmable Logic Controller. It was primarily used to replace relay control, marking the entry of industrial control into the digital age. 1971, European countries followed closely, developing their first PLC. The wave of digital industrial control began spreading globally. 1973, Japan introduced PLC technology and successfully developed its first domestic PLC. The Asian market began embracing this new technology. 1974, China initiated PLC development work and achieved industrial application by 1977, starting its exploration into industrial control automation. From the requirements in 1968 to the first PLC in 1969, in just 1 year, the industrial control field leapt from mechanical relays to digital controllers. This was driven by the urgent industrial need for efficient, flexible control. After over half a century of development, PLC has now entered the stage of intelligence and openness, becoming the core of industrial control systems. Compared to early relay control systems, modern PLC control systems have the following advantages: high applicability. They are adaptable to different industrial control needs. High noise immunity, industrial-grade design, stable operation in harsh environments. Functional perfect, so it can achieve logical and complex control. Easy to learn and use. Programming languages close to electrical control logic. Low power consumption, significantly lower than relay systems. Simple wiring, modular design reduces on-site wiring. Low failure rate. Good versatility. Unified programming standards across brands and series. Facilitate cross-device operation. Compact size, lightweight. Saves installation space. Easy to modify. Control logic can be changed by modifying the program. High reliability. Mean time between failures, MTBF, far exceeds relay systems, reducing downtime risk. With the advancement of Industry 4.0, PLC future development shows 3 major trends, such as edge computing nodes, AI convergence, and so on. Trend 1, edge computing nodes and the evolution of localized data processing architectures. Edge computing moves data processing from the cloud to on-site devices like PLCs. Enables local collection, local processing, local response. Take B&R's APROL Edge Gateway as an example. Its local processing achieves to 20 milliseconds rapid response, reducing network latency by 80% compared to traditional cloud processing. Crucial for high real-time requirements to avoid production errors or safety incidents. From a technical implementation standpoint, edge nodes adopt advanced containerized deployment, supporting Docker or Kubernetes orchestration systems, enabling engineers to rapidly deploy and update control programs. The storage architecture adopts a hierarchical caching strategy to ensure that the data is retained locally for 30 days, satisfying real-time processing requirements and providing support for later data analysis. Besides, edge nodes fully support OPC UA and TSN protocol stacks, which can convert multiple protocols, connect to on-site devices, and solve the problem of protocol islands. Trend 2, AI convergence, in other words, the smart upgrade of industrial control systems. It's the deep integration of artificial intelligence and industrial IoT, turning PLCs from simple control devices into intelligent decision-making devices. When it comes to hardware innovation, take Siemens S7 to 1500 terameters NPU module as an example. It has a built-in TensorFlow Lite runtime with an inference performance of up to 15 TOPS. It can directly run AI models right there on the industrial site to detect product defects and predict equipment failures. This module uses a modular design and supports algorithm hot updates. Model switching takes under 500 milliseconds. Engineers can update the AI algorithms without stopping the machines, so production won't be affected at all. For deploying algorithms, we use model quantization technology to adapt to the limited hardware resources of industrial equipment, cutting memory usage by 75%, making complex AI models operate smoothly on PLCs. It also supports federated learning frameworks. Multiple PLCs can jointly train models without sharing raw data. This not only protects data security, but also improves the model's generalization ability. For example, on multiple automobile assembly lines, PLCs can jointly optimize the welding quality inspection model through federated learning. This boosts inspection accuracy and keeps data within the factory. Trend 3. Open Source Challenge, also called the restructuring of the industrial protocol ecosystem, which has altered the way competition works in the PLC sector. On the technical route, there's a tug-of-war between open source and closed source approaches. For example, open source implementations of EtherCAT are promoting TSN-compatible solutions. These achieve a clock synchronization accuracy of plus or minus 20 nanoseconds, meeting the demands of high real-time control. Meanwhile, traditional manufacturers rely on hardware encryption chips to protect the intellectual property rights of their protocol stacks, maintaining their technical barriers. In terms of ecosystem development, open-source solutions have obvious advantages. They cut the access costs for small and medium-sized manufacturers and shorten the development cycle by 60%, letting more enterprises join in industrial automation innovation. But this has put pressure on traditional industry giants. Their hardware profit ratio has dropped to 45%, forcing them to shift from selling hardware to selling services. Now that we've covered the past, present, and future trends of PLCs, let's get a clear grip on what a PLC actually is. Programmable Logic Controller, or PLC for short, is a type of digital electronic system designed specifically for industrial use. You can understand its core functions from three aspects. First of all, it uses a programmable memory. This is the PLC's brain. It stores the instructions needed to carry out logical operations, sequence control, timing, counting, arithmetic operations, and more. Second, it uses digital and analog input and output interfaces to connect with industrial field devices like sensors and actuators and control the production process. Third, it's built to fit right into industrial environments. It can stand up to electromagnetic interference, vibration, high temperatures, and other harsh conditions, ensuring steady long-term operation. Simply put, a PLC is just a computer for the industrial field, but it's tougher and more focused on control functions than a regular computer. It can accurately direct machines to finish complex production tasks. The development of PLCs didn't happen overnight. It went through 4 key stages, and each step drove the upgrade of industrial control. Stage 1 was the early 1970s, when microprocessors were added to PLCs. That marked the first big leap in PLC technology. Microprocessors meant PLCs were no longer limited to simple logic control. They also gained computing, data transfer, and processing capabilities, boosting their control ability. Stage 2 was the late 1970s. Computer technology was fully integrated into PLCs, making them faster, smaller, and more reliable. During this stage, PLCs gained analog computing and PID control capabilities. Their cost-performance ratio improved, and they started to be widely used in the industrial sector. Stage 3 was from the 1980s to the mid-1990s. This was the fastest growing period for PLCs. Its annual growth rate hit 30 to 40%. During this phase, PLCs saw massive improvements in analog processing, digital computing, human-machine interfaces, and networking capabilities. Large-scale and ultra-compact models were developed. Special function units came into being, and human-machine interfaces and communication units were produced, all of which made it much easier to control industrial equipment. Stage 4 has been from the early 2000s up to now. PLCs have evolved toward intelligence, networking, and openness. They've integrated into the Industry 4.0 framework and deeply combined with edge computing, the Internet of Things, and artificial intelligence, becoming key nodes in industrial digital twins. There are many types of PLCs, and they're usually classified by I/O point count and structural form. When it is classified by I/O point count, it's based on the number of input and output signals controlled by the PLC. First up are small PLCs. They have fewer than 256 I/O points, feature a compact and rugged design, and come with only a few expansion modules. They're ideal for controlling individual machines or small-scale equipment. For example, with the Siemens S7200 Smart, they're often used for machine tools and the like. Next are medium-sized PLCs. They have between 256 and 1024 I/O points, can accommodate multiple plug-in modules, come with a full range of functions, and support complex logic control as well as basic network communication. The Siemens S7300, for example, is used to control certain sections of production lines. Last are the large PLCs. They have over 1024 I/O points and are equipped with complex process control capabilities, which has high storage capacity and fast processing speed, handles large networks and distributed control, such as the Siemens S7400. It is used for the overall automation of large-scale factories. Based on their structure, they are mainly divided into two types, unitary and modular. Compact PLCs integrate the CPU inside the casing, offering a small footprint and lower cost, such as the Siemens S71200, ideal for small applications. Modular PLCs use a bus to connect different modules. This allows for flexible configuration and easy expansion, like the Siemens S7300, perfect for medium and large systems, with flexible maintenance and easy upgrades. The working principle of PLC is the core of learning. It adopts a cyclic scan working mode, which continuously repeats three processes: input sampling, program execution, output refresh, similar to the human see-think-do cycle. First, input sampling. The PLC periodically reads the status of input devices and stores it in the input image area. For example, when input button I0.0 is pressed as shown in the courseware, the status of I0.0 in the input image area changes from 0 to 1. The input status is frozen to ensure data stability during program execution. Next, Step 2, Program Execution. The PLC executes the user-written program starting from the first instruction, sequentially performing logical operations based on the status of the input image area and the program. For example, in the forward control logic in the courseware, when I0.0 is pressed and I0.1 and I0.2 are not pressed, the program calculates the status of Q0.0 as 1. Last, Step 3, Output Refresh. After program execution is complete, the PLC stores the operation results in the output image area and then transmits them uniformly to the output devices to drive the field devices to act. For example, when the status of Q0.0 is 1, the output module turns on the KM1 contactor and the motor runs forward. This cycle repeats continuously. The scan cycle is usually at the millisecond level, ensuring the PLC responds to field changes in real time. For example, in machine tool control, the PLC scans every 10 milliseconds. It can quickly detect tool position signals and adjust the feed rate to ensure machining accuracy. PLCs are widely used in the industrial field because they possess characteristics that adapt to industrial requirements. First, it features high reliability and strong anti-interference capability. It adopts contactless logic operations to avoid mechanical wear of relays. The internal circuit is designed with electromagnetic compatibility to resist electromagnetic interference and power supply fluctuations. The mean time between failures is far longer than that of relay systems. Secondly, it has comprehensive functionality, is flexible in application, has strong expansion capabilities, and can perform a variety of functions. It can also increase I/O points and communication interfaces through expansion modules, adapting to different control requirements. Furthermore, it is easy to learn and use, convenient to program, and cost-effective. It uses programming languages close to electrical control logic, making it easy for electrical engineers to master. Programming software includes simulation and debugging functions, reducing development difficulty, and its cost is much lower than that of customized industrial computers. Additionally, system design and installation workload is small. Maintenance is convenient and modifications are easy. It employs modular design, reducing wiring workload. Faults can be diagnosed via programming software, improving maintenance efficiency. Modifying control logic only requires updating the program, adapting to changes in production processes. Finally, it is small in size, lightweight, and low in energy consumption, uses large-scale integrated circuits, saves installation space, and has low power consumption, reducing production energy consumption. PLCs have a wide range of applications, covering almost all industrial fields. They are mainly divided into 5 categories. First, sequential control. This is a classic application. It can replace traditional relay sequential control. For example, welding robot movements on an automotive assembly line are controlled by a PLC according to the program, ensuring accurate production rhythm. Second, process control. PLCs can control physical parameters like temperature, achieving closed-loop control through PID modules. For example, in a chemical reactor, the PLC collects temperature signals, adjusts heating power, and stabilizes the reaction temperature. Third, communication and networking. PLCs can communicate with other equipment, forming a distributed control system. For example, in a large brewery's central control room, the PLCs in various workshops are connected via a network for real-time data monitoring, enabling global optimization. Fourth, data processing. PLCs have functions like mathematical operations and can complete production data collection and analysis. For example, on a food packaging line, the PLC counts packaging quantity and qualification rate, generates reports, and uploads them. Fifth, motion control. PLCs precisely control motor drives through position control modules, providing precise control of the drive motor. For example, PLC controls the motor's motion trajectory in CNC machines, ensuring the dimensional accuracy of part machining. To deeply understand the advantages of PLCs, let's compare PLCs with relay control systems in 5 aspects. First, in terms of working mode, relay control circuits operate in parallel. All relays act simultaneously. A fault in one contact may affect the system. In contrast, PLCs use cyclic scanning, periodically checking the status of soft relays and controlling outputs in sequence according to the program. The action logic is clear and anti-interference is strong. Second, regarding reliability and maintainability, relay control systems have many mechanical contacts that are prone to wear, oxidation, and have poor reliability. Troubleshooting and maintenance are difficult. Conversely, PLCs have no mechanical contacts. They use industrial-grade components and have high reliability. Faults can be located through programming software, making maintenance convenient. Third, in terms of control method, modifying functions in relay systems requires rewiring, resulting in poor flexibility. In contrast, PLCs use stored logic. Functions are changed by modifying the program. They adapt to rapid adjustments in production processes. Fourth, regarding contact quantity, relays have a limited number of physical contacts. Complex controls require extensive stacking. In comparison, PLC soft relays have an unlimited number of contacts, which can be reused, simplifying control logic. Fifth, in terms of components, relay control systems are composed of physical hardware, subject to mechanical wear and capacity limitations. In contrast, PLCs are composed of electronic components. Soft relays do not wear out, have long lifespans, and offer large control capacity. Currently, there are many PLC brands in the global market. Next, let's learn about mainstream domestic and international brands and their representative series. Germany's Siemens is a global industrial automation giant. Its Simatic series is widely used. Models like S7 200 Smart, S7 1200, S7 300, S7 1500, and S7 400 can meet full scenario requirements. France's Schneider Electric's core is the Modicon series, such as M340 and TM218, known for reliability and strong communication capabilities. They are widely used in power and water treatment industries. USA's Rockwell Automation's Micrologics SLC 500 are widely used in automotive manufacturing and food and beverage industries. They are known for durability and system integration capabilities. USA's General Electric's RX3i and RX7i series PLCs focus on large-scale, complex industrial control and have advantages in metallurgy and aerospace fields. Japan's Mitsubishi's FX3U and Q-series PLCs are cost-effective and have user-friendly programming software. They are widely used in electronics manufacturing and machine tool industries. Japan's Panasonic's FPX C60 tons and other series are compact in size, suitable for small equipment control. China's Inovance's H2U Small Series and M600 Medium Series PLCs have a high localization rate. They are rising rapidly in new energy and robotics fields. China's Xinji's XC3 series PLCs are affordable and easy to use. They are widely used in small and medium-sized automation equipment. In summary, understanding the characteristics of different brands helps in selecting a suitable PLC model based on project requirements. To help everyone master this learning content, the task will be completed through group cooperation. The specific steps are as follows. First, before class, form groups of 4 and choose one topic from 5: PLC control technology, origin, development trends, working principles, main features, main application fields to research. During class, each group discusses around their chosen topic, organizing key knowledge points. Finally, each group selects one representative to give a rigorous and accurate presentation. Task evaluation uses a 100-point system, covering 4 dimensions. Teamwork, 20 points, assessing discussion, planning, division of labor, and participation. 7S management, 20 points, assessing work environment, item organization, safety, and cost awareness. Learning methods, 5 points, evaluating method effectiveness and applicability. Professional cognitive ability, 20 points, checking mastery of PLC origin, principles, etc. Professional practical ability, 35 points, assessing research, principle explanation, etc. I hope everyone can master the knowledge through group cooperation and develop teamwork and engineering practice skills. This lesson covered the background, birth process, development stages, definition, classification, working principles, features, and uses of PLCs. It compared the advantages of PLCs and relays, and introduced mainstream brands and future trends. Finally, 2 thinking questions are left. First, list other PLC brands and their characteristics. Second, point out occasions where PLCs are used in daily life. I hope everyone gains a clear understanding of PLCs through this lesson and lays a foundation for subsequent learning of the Siemens S7 1200 PLC. This concludes the course. Thank you, everyone.